Alright, so now I'm going to talk about integration by parts, which I find by far the more complicated and harder and longer method of integration. Use of substitution I found pretty simple and fun, but this is definitely not that. But enough about my whining, let's just start. Integration by parts we use to undo product rule of any derivative of integrals, whereas use substitution sort of for like chain rules. I'm going to start with the formula for integration by parts, and the formula is the integral of u dv is u times v minus the integral of v du. So basically u times the antiderivative of the dv term minus the antiderivative of the v term times the derivative of the u term. So now you may be wondering, what do we use to decide what our u term is and what our dv term is? Well, we have this acronym called LIPIT. So how LIPIT works is the first term, when you go down to LIPET, the first term that you encounter in your function is your u term, and the other term will be your dv. So LIPIT stands for logarithms, inverse trig, polynomial, exponential, and trigonometric. So now you're probably wondering how this list came to come in that order. Well, you're differentiating u and you're integrating dv. So if you'll notice, the bottom terms, which is what you'll assign dv, are the ones that are pretty simple to integrate. Trig functions is just memorization or use substitution. Exponential functions is usually just e to the x right here, and as you know, the derivative of e to the x is e to the x. The antiderivative of e to the x would be e to the x. So that's a really simple one to have as your dv. Polynomial, there's a power rule for finding integrals of polynomials, so yeah, that's also pretty simple. But inverse trig and logarithms are very complicated to find the antiderivative of. In fact, in order to find the antiderivative of these two, you have to use integration by parts within itself, so it's a very long process. So you don't want to assign those as your dv, and that's why we have them as our u. Okay, so now I'll show you an example. So say we're trying to integrate x squared sine x dx. So going down the list, we don't have any logarithms here. We don't have any inverse trig. We have a polynomial, which is x squared. So we're going to make that our u, and the other term, sine of x, our dv. dv equals sine of x, and u equals x squared. So du equals 2x, and sorry, let's get rid of this. V equals negative cosine of x. Now, following this formula we have here, the integral of x squared sine of x equals negative x squared x squared times, which is our u, times v, negative cosine x, so that gives us negative x squared cosine of x. Then we have to subtract the integral of v, which is negative cosine, and du, which is 2x times 2x. So now, just take the negative cosine of x, negative 1 from the cosine of x out, and we get negative x squared cosine of x plus the integral of cosine of x, 2x cosine of x. What you'll notice is that u substitution doesn't work for this either. So now we have to integrate by parts again. So you see what I'm saying by this process is pretty annoying and long. So this time it's also another polynomial and a trig function. So we're gonna make, sorry, I'm gonna fix my camera real quick. We're gonna make our u equal 2x and our dv equal cosine of x. So du equals 2 and v equals sine of x. So now we do the formula again, and we get negative x squared cosine of x from up there, from up here, plus 2 times v, which is sine x, 2 sine x, minus the integral of, sorry, my bad, 2x sine x, because our u is 2x rather than our du. My bad. I'm kind of tired, in case you haven't noticed. So 2x sine x minus the integral of v du minus sine x times 2. So using the constant multiple rule, we have negative x squared cosine of x plus 2 times x sine of x minus the integral of sine of x. We can do this because we can factor out a constant in the integral sign, and since both these terms have a 2, we have 2 times x sine x minus the integral of sine x. And what you'll notice is that we can actually finally take the integral of a sine, which is cosine, negative cosine, sorry. So now we have finally negative x squared cosine of x plus 2x sine x minus plus 2 cosine x plus c, our constant of variation, since this is an integral that doesn't have bounds, just to, so that was a very long process, and I feel like I want to give, even though this is a long process, since we have our u as a polynomial, we can do a different method of integration by parts, which is by far a lot easier, and this is called tabular method. And once again, I stress that it only works when u equals a polynomial. And the reason that is because if you keep taking derivatives of polynomials, you'll eventually get to 0, and the way tabular works is that's what we need. So how you do tabular is you make two columns, one of u and one of dv. So in your u column, you start out with your original term of what you make your u, which is x squared, and in dv you put your dv, which is sine of x. And in your u column, you just keep taking to the derivatives until you get 0. So 2x, 2, and then 0. And you keep, and you do the same thing for your sine x, for your dv, and go out the same number of terms you did for your u. So sine x, the antiderivative of that is negative cosine of x, and the antiderivative of that is negative sine of x, and the antiderivative of that is cosine of x. So we go out the same amount of terms. And next what you want to do is draw a diagonal line from the first term of the u to the one directly below it in the dv column. So I draw the line from x squared to negative cosine of x, I draw a line from 2x to negative sine of x, and finally a line from 2 to cosine of x. And next what you want to do is put a plus sign in your first line and then alternate the signs. So plus, minus, plus. So if say I had another line, I'd make that a minus, another line, make it a plus. So start on plus and just alternate those. Finally, you want to multiply the terms in the diagonal. So this one makes x squared minus cosine of x times negative cosine of x, which is negative x squared cosine of x. And this one makes 2x sine x. It's positive because two negatives make a positive. And this one makes 2 cosine of x. And now what you want to do is sum these three terms. So now that gives us negative x squared cosine of x plus 2x sine of x plus 2 cosine of x. And since we're finding the derivative, the integral of a function without bounds, we have to add the plus c. And what you'll notice is this is exactly the same thing as what we got when we did Lipit. So tabular method only works if you have u as a polynomial, but when you are fortunate enough to have that, it's a lot shorter and easier to do. In my handout, I included an example of taking the integral of inverse trig function and show how that uses an integration by parts. So I would definitely read that because you're gonna take a lot of, that's probably like almost a guaranteed question on either your test or the AP exam, taking the antiderivative of inverse trig, because it's like the easiest way to test integration by parts. So definitely keep an eye out for that. And thank you so much for watching these video series. Uh, I didn't do a very good job, in my opinion, on some of the topics, but hopefully you were able to learn something anyway. And I guess as a recommendation for doing this as your project next year, I kind of wouldn't recommend you to make a video lesson for your final project, because I feel like it can be kind of hard to teach something. It's a lot harder to teach something than it is to write a paper about it or whatever. So this is a new experience for me, but I feel like I could have done a better job, but I think I learned a lot through it anyway. Anyway, thanks for watching, and bye.